Now that we've learned several different techniques for integration, we want to be able to identify what to use when. You're going to be given several different integrals, and you have to decide which of these strategies you are going to apply. Now, one of the strategies that I left off is kind of an overall strategy that I want you to be thinking about, and that's how can you simplify? So we're always thinking about how we can simplify, whether that's algebraically, with a trig identity or whatever. How can we simplify these? So I want to go through and just talk about each of the examples that I've got up here, and then we'll work each of them out. So let's go ahead and start here with this one. I've got x plus 27 over x plus 3, x plus, or x minus 5. This one is a partial fraction one. So I'm going to go ahead and draw an arrow over here to partial fraction. There's a couple of clues. First of all, I've got a degree 2 in the denominator and a degree 1 in the numerator. This is what we call a proper fraction, smaller degree in the numerator. The other clue is that I really can't use a u-substitution. My first and foremost, if I can't just use a common integral tool, my first and foremost goal is to either use a common integral, power rule, or a u-substitution. If I can't, then I've got to use one of the strategies 3 through 7. And in number 1, we're going to need a partial fraction decomposition. Okay, let's go ahead and take a look at number 2. So in number 2 here, I've got x plus 2, x minus 1. Now I do have a product, which would maybe be an integration by parts, but remember you're thinking, can you simplify this? Yeah, of course, I can just FOIL this guy out, and I get x squared in my integrand plus 2x minus x, so plus x minus 2, which becomes a really nice power rule. So this one's going to go up here to number 1. The next one, number 3, I've got 3x e to the 2x. So this one really, to me, boils down to one of two choices. Because I've got a product, and I'm thinking of that product as the x times the e to the 2x. So it could be either a u sub, but if I tried to do a u sub, my u would be 2x. So my du would be 2dx, and I wouldn't be able to take care of the x there. So since a u sub won't work, that means that we would be left with instead the integration by parts. So the clue there for the integration by parts is that you have a product and you can't use a u sub. So really, we try and use the u subs whenever we can. Okay, so the next one, number 4. So in number 4, let me go ahead and grab a black pen for number 4. So in number 4, I've got x minus 2, x plus 3. There really isn't anything that I can do in terms of a partial fraction decomposition. Well, maybe there is one thing, and that's just to split this up into 2 separate fractions. But we really don't think about this as a decomposition. So minus 2 over x plus 3 dx. Now I could do this and then use a u-substitution, but instead I'm going to keep it as simple as possible. I'm going to use a u-substitution. I really don't want this x plus 3 in the denominator. I want a single term in the denominator, and I can accomplish that by using u as x plus 3. du then is the dx, but I can replace this x right here with a u minus 3 equals the x. So I'm able to accomplish a u substitution. So this one, and I had to think it through a little bit, but this one's going to be a u substitution. Now let's go ahead and move on over to the other side. On the other side, I've got, let's call this one number 5. So number 5, I've got e to the 2x cosine e to the 2x. Yeah, I do have a product, but I'm only going to use integration by parts if I have to. Can I use a u substitution? Let's go ahead and try. So u is equal to e to the 2x, which means that du would be e to the 2x with the 2 out in front. So 2e to the 2x, and then dx. So that does take care of everything in my integrand. So this one would be a u substitution. So number 5 is a u substitution. Number 6 here. So in number 6, I've got a radical x squared minus 9. Now the first thing that I would try would be a u substitution on the x squared minus 9, but I would need just an x term in order to make the u substitution work. Well, because I have either a sum or difference of squares, so a sum or difference of squares, This tells me that I can probably use a trig sub. So a sum or difference of squares leads me to using a trig sub. Okay, last but not least here, number 7. So in number 7, I have dx, x natural log of x. And I do see these layers, which makes me want to use a u substitution. And the layers that I see are the radical and the natural log of x. So I'm going to go ahead and attempt a u sub. So u is equal to the natural log of x. And that means that du would be 1 over x dx, which I could also think of as dx over x. And that would replace the other part of my integrand. So this one becomes a u substitution as well. So as I'm working through my strategy, let me go ahead and grab a highlighter here. As I'm working through my strategy, I am simplifying as I go through. I'm looking for, of course, common integrals and the power rule. That was all I needed for number 2. And my first attempt, unless it's something obvious, is to do a u substitution. I don't want to have to do a trig sub or an integration by parts unless I absolutely have to. Then I start looking for clues for 3 through 7. Integration by parts, I really am looking at a product for that integration by parts. Let me go back to my pen here. And then for the trig integrals with trig identities, these are their own form of u substitution. So we'll see some of those as well. Trig substitutions, this would be a sum or difference of squares. Partial fractions, we're certainly looking for a rational expression that we can't do a u substitution on. So some polynomial over a polynomial there. And then we didn't have any examples of improper integrals, but that's where we have unbounded limits of integration. Okay, let's go ahead and move through these. The first one, I've got that difference of squares right here. So my strategy is a trig substitution. Because I have x squared minus 9, that means that I'm going to use this u sub. X is equal to a secant theta. A is equal to, so a is equal to 3. So x is equal to 3 secant theta, and I can write that further as x over 3 equals secant theta. I know I'm going to want to construct my triangle, so let's go ahead and flip this. 3 over x is equal to cosine theta. And I need to be able to replace everything that I see in this integrand. So as I'm looking to replace everything, I can already replace the x to the 4th. That would be x to the 4th would be, I'm actually using this one. So x to the 4th would be 3 to the 4th secant to the 4th theta. So I can replace the x to the 4th. I also need to replace a dx. Let's go ahead and take dx here. Dx is going to be equal to 3 secant theta tan theta. So I've got the dx replaced. The 27 is just a constant multiplier, and I also need the square root. I'm going to get to the square root with my triangle. So I'm going to use my cosine. So I've got theta here. Cosine is adjacent over hypotenuse. So my adjacent side is 3. My hypotenuse is x, which means that my opposite side is going to be x squared minus 9 inside the square root. I am looking for the x squared minus 9 inside the square root, and I can most easily get there by combining the 3 and the radical x squared minus 9, by combining my adjacent and opposite sides. That's going to be a tangent. So I'm going to say that tan theta is equal to opposite over adjacent, SOHCAHTOA, and this is the square root of x squared minus 9 divided by 3. So I can replace 3 tan theta with the square root of x squared minus 9. So I've got this one replaced as well. Let's go ahead and do the trig substitution now. So taking my integral over here and replacing everything in terms of theta, the 27 can come out in front. First, let's do that square root of x squared minus 9. That is this one right here. So that's going to be a 3 tan theta over x to the 4th. X to the 4th is right here. So that's going to be a 3 to the 4th secant to the 4th theta. And then finally, I need my dx. So my dx is here, and that's times 3 secant theta tan theta d theta. Let's go ahead and simplify what we've got. Now I've got a secant to the 4th, or sorry, I've got a 3 to the 4th. I have a 3 and a 3 here, so let's write this as 3 squared times 3 squared. I can cancel these 3's, and then 9 into 27 is going to go 3 times. So I have a 3 here. I can also cancel a single secant. Okay, so what's that going to give me? I have a tangent squared in the numerator. So tan squared theta in the numerator. In the denominator, I have a secant cubed. Secant cubed. Theta, d, theta. I'm going to go ahead and write everything in terms of sines and cosines, simplifying what I can. Tangent is sine over cosine. So this is going to be sine squared theta over cosine squared theta. Secant is the reciprocal of cosine. So I can write that secant as cosine in the numerator, but that's going to be a cosine cubed in the numerator, divided by 1 d theta. I can cancel a single cosine, and this actually works out really nice. I can cancel, 2 cosines, leaving me with a single cosine. So I end up with 3 integral sine squared theta cosine theta d theta. This is going to work out, this is going to work out really nicely for us because I can use a u substitution here. I'm going to let u equal sine theta. du is cosine theta d theta. Let's go ahead and put that on the next page here. So we had 3 sine squared theta cosine theta d theta. U is equal to sine theta. So du was cosine theta d theta. That takes care of everything inside of our integrand. So I can rewrite all of this now in terms of u, doing a u substitution, and I have u squared du. Continuing, I can take that integral, 3 from the outside. The power 2 goes up to 3, so I get times 1/3 u cubed plus c. But I can go ahead and put u back in. So I'm going to go back to theta. We had gone from x to theta to u. I'm going to take that first step back and go back to theta. That's where I'm at right now. My 3's cancel. I have u cubed, but u is sine theta. So this is going to be sine theta cubed plus c. Now I need that triangle in order to figure out what sine theta is. So back to my triangle here, the sine of theta, sine is SOHCAHTOA, so that's going to be opposite over hypotenuse. So the sine of theta is going to be radical x squared minus 9 over the hypotenuse, which is x. So using that triangle, the sine of theta is opposite over hypotenuse, which is the square root of x squared minus 9 over my hypotenuse, which was, there it is, x. So now I can go back to x, completing that last undoing of my substitutions. This is going to become my answer now. Sine of theta is this guy right here. So it's going to be the square root of x squared minus 9 divided by x, all cubed, plus c. Now I can simplify that. This square root is really a 1/2 power. So I can think of that as, let me write it in green actually. I can think of that as x squared minus 9 to the 3/2 or 1.5 power, which is going to be x squared minus 9. X squared minus 9 to the 1/2 power. So I can simplify this just a tiny bit and write this as, I can pull out a full x squared minus 9, and then I have 1/2 power. So I'm going to leave that inside the square root. My denominator is an x, also cubed, so I'll write that as x cubed, and then plus a c. This is our answer. You'd want to show all of those steps in order to get full credit. Next one, I've got this dx over x natural log of x. Now, what I'm really focusing in on here are the layers, and I've got a square root symbol here, and then inside I have the natural log of x. And this is going to cause me to use a u-sub. U-sub is always a great first attempt before you get into some of those other strategies. Let's go ahead and attempt the u-sub, and I think we've already done it actually, so we know it works. U is equal to the natural log of x. I also need du. Du is 1 over x dx, also known as dx over x. dx over x is right here. Now this one also has a couple of limits of integration. So I need to figure out what u1 and u2 are. u1, my lower limit, is going to be the natural log of x. Natural log of 1 is 0. u2, which is my upper limit, is the natural log of x, the natural log of e to the 7. Natural log and e undo one another, and I get 7 back. Those are my limits of integration. Let's go ahead and rewrite this now in terms of u. So my integral is going to go from my u1 to my u2, so 0 to 7. dx over x is going to get replaced with my du, so du here. And then I've got the square root of the natural log, so that's going to be the square root of u. Writing this so I can do a power rule, this is integral 0 to 7. Now for the u to the -1/2 du. I can use a really nice power rule there. -1/2 plus 1 is +1/2. Reciprocate that, I get a 2 to the 1/2, evaluated from 0 to 7. So this is going to give me 2 radical 7, because u to the 1/2 is the same thing as the square root of u. So radical 7 minus radical 0. And we get 2 radical 7 for our answer. Okay, next one. So the next one, it is a product. So as I'm thinking about this, like one of the thoughts might be, gosh, it's a product, and a lot of products turn out to be integration by parts, but I want to try a u-substitution first. My layers are here. I have an outer layer of cosine and an inner layer of e to the 2x. I'm going to attempt the u-sub first, and it's going to work for me. So I'm going to let u equal e to the 2x. du, I get e to the 2x back, but I need to take the derivative of 2x as well. So I get 2 e to the 2x dx. That's going to replace this as well. So 1/2 du is going to replace that e to the 2x along with the dx. So my strategy here is the u-sub. Let's go ahead and do that u-sub. So this is going to be equal to u integral of, I have my cosine. So it's going to be cosine of u. And then everything else is going to be the e to the 2x, the dx, the e to the 2x, the dx is going to get replaced by a 1/2 du. This is a really nice integral. I can bring that 1/2 out in front. I'm just doing a nice common integral of the cosine of u du. The antiderivative of cosine is sine. So I have 1/2 sine u plus c. Now here I just went from x to u, so I need to go back to x. So equals in terms of x, 1/2 sine u. Let's go grab u. u is e to the 2x. So the sine of e to the 2x plus c. There's no other simplifying that we can do, so this is our answer. Next, integral. So for this one, there's really not a u-sub that I can do, at least not right off the bat. I do want that denominator, x plus 3, to change into a single term. Now you could try splitting this up into 2 separate fractions, but I want to do the u-sub first. So my u-sub would be my first try. If that didn't work for one like this, I would end up using partial fractions. But I'm going to go ahead and try the u-substitution first. I really don't want to sum in that denominator. It's so much easier if I have a single term. So if I attempt the u-sub, u is going to be that x plus 3. du then is dx That takes care of this one, but it leaves me with the x minus 2. I can solve for x here. U minus 3 is equal to x. So as I put this all together, then I can replace everything that was in terms of x in terms of u now. So I've got this here. This first x that I come across in my numerator, x, that's going to be a u minus 3. So u minus 3 minus 2. In the denominator, I have a x plus 3. X plus 3 is u. So x plus 3 is u. And then dx gets replaced with du. Let's go ahead and simplify this a little bit. And I've got u minus 3 minus 2. So that's going to be u minus 5 divided by u du. Now I'm going to split it up into two fractions. U over u minus 5 over u, all du. This first one is just a 1. So as I think these through, actually I'm going to write them as two separate integrals. This is going to be 1 du minus, I can pull the 5 out in front, integral of 1 over u du. Integrate that 1 du and I just get the variable back u minus 5. The integral of 1 over u is the natural log of u. I don't know if u is positive or negative, so I better put absolute value bars around that one, plus c. I have gone from variable x to variable u, so I need to get myself back to variable x. U is equal to, where's my u? There it is, an x plus 3. So wherever I see a u, I'm going to write an x plus 3. So this is getting myself back to x. Minus 5 natural log, there's another u, x plus 3, and then, of course, plus c. This is my answer. You can't combine the 3 and the 5 because the 5 is being multiplied, so there's really nothing else that you can do but maybe write it all in the same color, but this right here is your answer. Okay, number 5. In number 5, I've got a 3x e to the x. This is actually pretty similar to the last one that we saw. We do have a product here, so I can put a multiplication symbol right there between the x and the e to the 2x. I could attempt a u sub, and if I did that, u would equal e to the 2x. du would be 2e to the 2x dx. I don't have all of that in the rest of my integral. So I'm going to abandon the u-substitution. That would have been nice if that worked. But because I have a product and u-sub didn't work, instead I am going to use by parts. To do my integral by parts, the integral of u dv is equal to u times v minus the integral of v du. Let's go ahead and identify what our u and our dv are going to be. I really want to break the x down so it goes away. So I'm going to let u equal x. Du then is equal to dx. I also need to identify dv. So I'm going to let dv be the e to the 2x dx. I'm going to find an antiderivative to get to v. To find my antiderivative, it's going to be 1/2 e to the 2x, and then just the dx. So for this one, you can take the derivative to make sure that it gets you right back to dv to make sure that you're on the right track. We are on the right track. So let's go ahead and apply our integration by parts. I'm going to start with u times v. So u times v is going to be x times 1/2 e to the 2x. This is u times v minus the integral. So minus the integral of v, which is 1/2 e to the 2x, du, which is dx. So this is minus the integral of v du. We've got a really nice integral to go ahead and take. Nothing to simplify over here. So I've got just x divided by 2 maybe, e to the 2x, minus, I can bring that 1/2 out in front. Let's go ahead and find the antiderivative of e to the 2x. That's going to be another 1/2 e to the 2x, and then plus a c. I can simplify this guy just a tiny bit. This is x over 2 e to the 2x minus 1/4 e to the 2x plus c. Okay, number six. Number six is a pretty obvious partial fraction decomposition, because I have that denominator factored out for us. There's really nothing that you could attempt for a u-substitution that's going to get you anywhere. So we're going to go ahead and dive into the partial fraction decomposition. I'm just going to grab the integrand and work on that partial fraction. So I've got a denominator of x plus 3. That's going to have a constant numerator a, plus a denominator of x minus 5, constant numerator b. So comparing just my numerators, x plus 27 from the original integrand, that's a 27, is equal to a times x minus 5 plus b times x plus 3. I'm going to be able to solve this by zeroing out, and I can zero out by letting x be 5 for one case and x be negative 3 for the second case. Let's go ahead and start with x equals 5. So when x is equal to 5, I get 5 plus 27, that's 32. A is going to zero out, and then I get b times 5 plus 3, so b times 8. I'm going to go ahead and divide both sides here by 8, and b is equal to 4. Now let's go ahead and find the next one. So now I'm going to let x equal negative 3. When x is equal to negative 3, negative 3 plus 27 is 24. On the other side, I've got a times negative 3 minus 5, which is negative 8, and the b cancels out. Divide both sides here by negative 8, and we get a is equal to negative 3. Putting this together, I can come up with my integral. So my integral is going to look like this. So I'm going to have an a over x plus 3. So that's going to be negative 3 over x plus 3 plus b is 4 over x minus 5. And this is all dx. These are natural logs. The negative 3 can pull out in front, so you can think of these as individual integrals, but I'm going to go ahead and do it all in one step. The 4 can pull out in front of its natural log. So I end up with, I'm actually just one step away from my answer here, negative 3 times the natural log of absolute value x plus 3, plus the 4 can come out in front of the natural log, so natural log, absolute value x minus 5, and don't forget your plus c, since that's an indefinite integral. And that is the answer. Okay, last but not least. So on this one, yeah, we do have a product. But remember that overall strategy that I wrote down on top of all of the steps was to simplify. This one can be simplified. I can FOIL this one, and I don't need to use any techniques other than just some really nice power rules. So I'm going to go ahead and just FOIL this. Let's multiply it out. As I multiply it out, I get an x squared. Outer is a negative x, inner is a 2x, so that's going to be plus x minus 2 dx. Just a really nice power rule on each of these terms. X squared becomes a 1/3 x cubed. X to the first becomes x to the second with a 1/2 out in front, so x to the second minus 2x, and then of course plus c. As you are thinking back through those strategies, let me grab them. There it is. So as you're thinking back through those strategies, it's kind of a mess, simplifying, that is your very first line of attack, right? And then you're focusing on, can I just do something simple, like a common integral, maybe a power rule, or can I use the u-substitution? If you can't do one of those things, then go on and see if you can identify one of the other techniques of integration.